In this lecture, we continue with our discussion on part of speech tagging of words in a sentence. We have remarked many times that part of speech tagging is the first fundamental operation on raw text, and subsequent stages of natural language processing like phrase detection, parsing, semantic role labeling and so on follow after part of speech tagging. This is also a very nice problem to illustrate statistical natural language processing, the application of machine learning on natural language problem. All right. So, as is shown in the slide now, part of speech tagging is a process that attaches each word in a sentence with a suitable tag from a given set of tags. The set of tags is called the tag set, and one of the very standard tag sets is the pen tree bank, which we show in the next slide. But before that, just some small remarks. We are saying that part of speech tagging is the process of attaching tags on the words of a sentence. So, the thing to note here is this entity called tag, which is like a label on each word. What these labels are, we are going to see in a minute. All right. So, the words are given these labels, and these are very informative for subsequent stages of processing. Progressing with our discussion, this is an important slide which shows the pen tree bank tag set. It is a sample. There are about 30 tags, and we show here a few of them, maybe about 10, and what is shown here are these labels. So, the first label here is CC, which is a short form for coordinating conjunction. The example of that is Jack and Jill. So, this is a phrase Jack and Jill, maybe they go up the hill, and this CC is attached to the word and, which is a conjunction joining Jack and Jill. So, and underscore CC shows the part of speech tag of and. The next one is CD or cardinal number. So, if we look at this phrase 4 children, 4 is a numerical adjective qualifying the noun children, and this is a cardinal number. CD is attached here. If the word was fourth, the fourth child, TH is added, then the part of speech tag would be the tag for ordinal number. So, that indicates an order. So, ordinal number tag would be placed. DT is the determiner, example the underscore DT sky. X is existential there as opposed to an adverbial there. Here the example is there was a king. So, there underscore X was a king. This there note is a pleonastic. It is a pleonastic. It is a vacuous subject. English sentences demand a subject to be compulsorily present. So, this there is given the tag EX existential as opposed to the adverbial there. FW is the foreign word. Here is a sentence Shabd in Devanagari, underscore FW indicating it is a foreign word. Shabd means word. So, we are explaining the meaning of this string sha, half ba and the. So, whenever the text of a language contains a string written in the alphabet of the foreign language, then we always place the tag FW. However, if Shabd was written as SHABD, okay, so in this case this would be an absorption of a foreign word transliterated into the language of the text. In that case, Shabd would be a noun and the noun tag would be placed on this. So, note the difference between shabd written in Devanagari and shabd written in English. When written in Devanagari, embedded in English text, it is the foreign word underscore FW, otherwise it is the part of speech that it has in that sentence. IN is preposition or subordinating conjunction. So, for example, play with ball, with underscore IN is the entity here and IN is the tag for with. This can also be used for subordinating conjunction. An example we can see later. JJ stands for adjective. Many times people have wondered where this JJ is coming from. Adjectives, it could be abbreviated as AD or ADJ, but why JJ? So, the example of that is fast underscore JJ car, fast car, it is an adjective. One conjecture is that adjective is often pronounced as adjective, okay, and it has two J sounds adjacent to each other, and most likely that gave rise to this two letter tag JJ. JJR is adjective comparative. So, fast car was the previous example, now it is faster car, okay, faster compared to another car, and this is underscore JJR. JJ is adjective superlative. So, fastest car JJS, fastest underscore JJS. LS is least item marker. For example, somebody is proposing to buy these grocery items, bread, butter and jam. The listing is given here 1 bread, 2 butter, 3 jam. So, 1 underscore LS, 2 underscore LS, 3 underscore LS, they are the tags for these list item markers. MD is the modal. This is the sentence here, you may go as opposed to you go, and may here is the modal auxiliary and is given the tag MD with an underscore. NN is probably the most important tag, which is the noun tag, which is used for singular or mass. So, water underscore NN. NNS is plural noun, boys underscore NNS. If you are wondering why there is a separate tag for NNS, note that in English most nouns can be used as verbs and the third person singular form of a noun and the plural of a verb and the plural form of a noun are often identical. So, if I say plays, it is not clear, is it multiple plays, many plays in the sense of drama, let us say, or is it the third person singular form of the verb play. N and P is proper noun singular. So, John underscore N and P is the proper noun. Okay. So, this illustrates some important points in this tag set. If you have paid attention to the tags, then you would see that lot of care has gone into deciding how to designate the tags properly. Okay. For example, there is a very subtle discussion on why plural nouns should have a separate tag compared to singular noun. Singular noun is NN, plural noun is NNS. Okay. And the reason for that, as I said, is that almost all English nouns can be used as verb. Play can be a noun meaning a dramatic performance, or play could be the act of playing, which is a verb. Now, if we see an isolated word in the text in the form of plays, then we would not know whether this is a plural noun or is it the third person singular form of play. The task of part of speech tagger is to place the correct tag on the word. So, the part of speech tagger uses limited context window and places the tag on the target word. Now, if this distinction is not made between singular noun and plural noun, and in the part of speech tagged corpus which is used for training, if we have many, we typically have many singular third person singular number verb forms, and we also have many plural nouns. If noun and plural noun is not cleanly separated, okay, then the part of speech tagger will get very often confused between the third person singular number form of the verb and the plural form of the noun. We will analyze this rather subtle issue with examples later. So, the point I am making is that when a part of speech tag set is designed, normally very experienced people with a lot of insight into how language operates, as well as how a computational system, in spite of its many limitations, is required to do this labeling. With this kind of experience, people discuss part of speech tag design. We in India have come up with a part of speech tag set for pan Indian languages, languages of northern India, Indo-Aryan family, languages of southern India, Dravidian family, languages of the northeast, Tibeto-Burman family, and Austro-Asiatic languages, namely Munda and Khasi. So, we have tried our best to come up with a tag set for Indian languages, which will be used for annotating data and subsequently doing natural language processing. Okay. So, I hope you understand the importance of designing a tag set with lot of insight and correctness. Let us proceed. So, we have already looked at a number of examples with words and their part of speech tags. Now, part of speech tag task is essentially a disambiguation task. Look at this sentence here. In English, we have this sentence, I bank on the river bank for my transactions. I concede that this is not a very natural sentence, it is a rather artificial sentence, but it illustrates the points I would like to make. The first bank is a verb, this means depend. I depend on the bank, this is a noun. On the river bank, this is also a noun. The third bank is also a noun for my transactions. So, the first level disambiguation task, which is executed through part of speech tagging, is the disambiguation of categories. This first bank is verb, other two banks, bank 2 and bank 3 are nouns. Now, this disambiguation is simple, but crucial for subsequent stages. Another disambiguation which will have to be affected is the disambiguation of second bank, bank 2 and bank 3. The first bank is the place where financial transactions take place. The second bank is the embankment, the landscape by the side of the river. So, this disambiguation is known as word sense disambiguation. It is possible to have same part of speech for a word, but the senses can be different. So, the first bank is a verb, other two banks are noun. This the ambiguity is not only characteristic of English, we see it in Hindi and many other languages. For example, the word khana, it can be a noun which means a food, or a verb which means to eat. Mujhe khana khana hai, the first khana is noun and the second khana is verb. We can also look at this nice example, Ram acha gata hai, Ram sings well, and Ram acha ladka hai, Ram is a good boy. So, here you can see that the only word which is different between the two sentences is gata and ladka. Acha gata hai, gata is a verb. So, acha is an adverb qualifying this verb. Acha ladka, ladka is a noun. So, acha here is an adjective for the noun. So, Ram acha gata hai, Ram acha ladka hai, first acha adverb, second acha adjective. So, the part of speech tagger has to disambiguate this. If you say that this disambiguation is not difficult, because you see the adverb is followed by a verb, the adjective is followed by a noun, then you might be misled into what is called false positive and false negative, which we have discussed last time in the lecture. I would just like to remind you that between acha gata you can have some amount of text. Ram to acha hi gata hai. So, this rule that an adverb should be followed by a verb will not hold true here. The rule will have to be made more robust. Similarly, Ram acha ladka hai, here also we can introduce a particle. Ram to acha hi ladka hai. Okay. Ram wo acha ek ladka hai. So, you can have text in between adjective and noun, and therefore, the rule will have to be made more robust. We have more than one problem in this sentence. Hai, look at the word hai. Ram acha gata hai and Ram acha ladka hai. The first hai is a helping verb for gata hai. It carries the tense information, gender, number information also. So, Ram acha gata hai. If it was Sita, Sita अच्छा गाती है, लड़के अच्छे गाते हैं. So, है form would change. If the tense was past tense, Ram अच्छा गाता था. So, auxiliary verbs plays an important role. It carries information about gender, number, person. This auxiliary verb. Ram अच्छा लड़का है. Here this verb is, this है is not an auxiliary verb, it is not helping another verb, it is called a copular verb. Copular verb also carries the information of gender, number, person, tense and so on. So, it is very difficult to distinguish between V cop and V ox, unless the word morphologically changes in these two situations. From the context, it can become very difficult many times. We will see examples later, disambiguation examples. Now, we discuss the process of part of speech tagging. This is a computational process. So, we have understood what the problem is, and now we are entering the computational discussion. We would like to understand how one could make an algorithm to produce these labels automatically. That is the task. So, the process is that list all possible tag for each word in the sentence and choose the best possible tag sequence. We have an illustration here. People jump high is a sentence. People can be noun or verb. Jump also can be noun or verb. High can be noun, verb, adjective. And we actually start with probabilities. So, people jump high will finally get this label. If the program is working correctly, it should get the label noun, verb and adverb. Actually, high can be an adverb also, okay, noun, verb and adverb. However, each word has multiple part of speech tags, and we will choose that tag sequence which has the highest probability. This is where we have a probabilistic approach. So, noun, verb, adverb tag will be the highest probability tag here. This is illustrated here. People jump high. So, this hat symbol is a important special symbol which is at the beginning of a sentence. Dot is again a special symbol which is at the end of a sentence, also called full stop. And for each word we place all possible tags as columns of tags on the words. Okay, so, people can be noun, verb, adjective, adverb. Jump can be noun, verb, adjective, adverb. High can be noun, verb, adjective, adverb. So, of course, you will object saying that people can never be an adverb, jump, how can it be an adjective, and so on. But this is only for the purpose of keeping the discussion simple and also illustrating how a simple algorithm would work, how a first cut algorithm would work. The first cut algorithm will not try to be intelligent right from the beginning. It will try to take all possible options or all possible tags for each word and then do a disambiguation or selection. So, if you look at this picture here, then for hat symbol, conventionally the tag is hat itself. So, for the hat symbol hat, people it can have all these 4 possible tags, so which is from the whole tag repository. Of course, people cannot be an adverb. So, this will come out to be probability 0. Jump can have all these tags, high can have all these tags. Now, when we connect all these tags together, okay, so this hat is connected to 4, N is connected to the 4 tags after it, V is connected to all the 4 tags after it, A similarly to all the 4 tags, R again to all the 4 tags. So, from here you can see 16 arcs go to these 4 tags for the next word. Similarly, from here there would be 4 into 4, 16 tags going into the next word's tags. So, this way we will define a graph, and our part of speech tagging problem, our part of speech tagging determination problem becomes finding a path through this whole graph, and this graph is the set of labels which would be placed on the words. Now, this graph traversal before we begin discussing the mathematical aspects, this graph traversal would finally find out the best possible tag sequence, the best possible labels for the words. What does this best possible mean? The best possible means the highest probability path from the hat symbol to the dot symbol. So, this highest probability path taking only one label per word is found out by the argmax computation. Okay. So, the best possible path here means the highest probability path. So, this mathematics is based on an argmax computation on which we have already spent quite an amount of time, and you will see that these fundamental ideas are brought to bear here. So, the best tag sequence we call as T star. T star is the best possible tag sequence. T star is found out from argmax of P T given W, where W is the word sequence and T is the tag sequence. So, if we place the tags on the set of words, then we have the sequence T and the word sequence is W. Here we apply Bayes theorem and we convert this expression into P T into P W given T. Now, this is also an old point discussed many times in previous lectures, that it is the problem which determines whether we should apply Bayes theorem or not, and thereby adopt a generative approach or a discriminative approach. Now, in this case the part of speech tag is determined through a generative approach. P T given W is converted to P T, the prior probability of the tag sequence, into P W given T, the likelihood probability of the word sequence given the tag sequence. So, this particular part may seem counterintuitive or unintuitive. One would think, what is this P W given T, because our very natural thinking about this problem is that given the word sequence, we would like to find out the tag sequence. However, as we remarked before, we convert this probability into these two parts, prior probability and the likelihood, and the prior probability acts as a nice filter to eliminate bad possibilities. So, this tag sequence P t is a representation for highly likely tag sequences as learned from the corpora. Okay. So, this point I suppose is clear to you. We have the prior probability, which many times acts as a model, okay, an ideal model for the label sequence that we produce. So, the P t part in the formula is a filter which helps isolate bad tag sequences and which gives weightages to good tag sequences. We understand this in a minute. The only counterintuitive part there is the P w given t, and that came because we wanted to apply Bayes theorem, and we will have to make some engineering judgments, take some engineering steps to make use of this expression P w given t. So, let us go ahead with the mathematical formulation. P t is written as P t 0 equal to hat, followed by T 1, followed by T 2, followed by T 3 and so on, until we have T n plus 1, which is equal to dot. Okay. So, we have here this tag sequence T 0, T 1 up to T n plus 1. This now can be broken down into a number of expressions, number of probability values, by applying what is called the chain rule, okay, which is a fundamental operation in probability. So, what we have done is that we have applied Bayes theorem, first fundamental operation, and the second fundamental operation is this chain rule, which is P t 0 into P t 1 given T 0, P t 2 given T 1 T 0, P t 3 given T 2 T 1 T 0 and so on, until we meet our last expression, which is P t n plus 1 given T n T n minus 1 up to T 0. Okay. So, this whole probability of the sequence is converted into probabilities of single labels given the preceding tag labels. All right. So, Bayes theorem applied, chain rule applied. Now, we apply what is called the Markovian assumption. Okay. And the expression that we have written here in the last line, P t I given T I minus 1, I going from 1 to n plus 1. This actually is a Bigram Markov assumption. What does it say? It says that fine, apply the chain rule, get the expressions, sub expression, the constituent probability values. However, these terms are very complicated to compute. So, P t n given T n minus 1, T n minus 2 up to T 0, we have to deal with n terms here in the conditioning part. What the Markov assumption is saying is that disregard anything which is very distant from the current tag. Okay. If the current tag is extremely far away, it does not have influence on the tag at the current position. So, P t 2 given T 1 T 0 is okay. We are saying that at the second position the tag is T 2 depending on the two tags just before it, okay, and anything beyond that is not useful to compute, to consider. So, if I take P t 5 for example, the tag at the fifth sequence, the only influencing factor on this is T 4 and T 3, only the first two previous tags. Here we have given a very simple expression, we have made what is called the Bigram assumption. We are saying that each tag depends only on the previous tag, on the tag coming before it, which is the conditioning part. So, I would present you with a small exercise and request you to do this to be convinced of the Bigram assumption or the Markovian assumption. So, the exercise is this: take a tagged corpora, for example, John laughs loudly. So, here the tags are John, N and P. Laughs is a verb, which is a main verb VM. Loudly is adverb RB. So, take a tag corpus, you will have this kind of tags along with the words. After this, from this tag corpus, compute n grams or compute P T n given T n minus 1, T n minus 2, T n minus 3 up to T 0. Okay. This we are saying is almost equivalent to P T n given T n minus 1, T n minus 2. This is trigram Markov assumption. So, what I request you to do is take P T let us say 5 and T 4, T 3, T 2, T 1, T 0, which you know is equal to count of the pattern T 0, T 1, T 2, T 3, T 4, T 5 divided by count of T 0, T 1, T 2, T 3 and T 4. If our assumption is correct, if the Markov assumption is correct, we will see count of T 0, T 1, T 2, T 3, T 4, T 5 divided by count of T 0, T 1, T 2, T 3, T 4 will be approximately equal to, we take it on the next page, T 5, that count divided by count of T 3, T 4. All right. So, this whole sequence T 0 to T 5 divided by T 0 to T 4 is approximated as T 3 to T 5 and T 3 to T 4. Okay. So, that is the Bigram assumption, and if our Markov assumption is correct, these two counts should come out to be approximately equal, telling us that we for a particular tag at a position or for a tag at a particular position, we need not consider any word which is beyond a certain distance. That is the meaning. Okay. So, this you should verify from a training corpus. We will mention important corpora, tagged corpora towards the end of the lecture, and it should be possible for you to verify this quite easily. But you should do this to be convinced of the operation of the Markov assumption. All right. Proceeding further, we see that P t is equal to this expression, and after making Bigram assumption, it comes out to be equal to P t I given T I minus 1, I going from 1 to n plus 1. Okay. So, this first part of the expression, the prior probability, comes out to be product of Bigram entities. P T I T I minus 1 is nothing but count of the number of times T I is followed by T I minus 1 divided by number of times T I minus 1 appears. All right. We move on to the next probability, which is the lexical probability. So, P w given T is shown here, which is equal to P w 0 given T 0 to T n plus 1. T 0 to T n plus 1 is nothing but capital T. P w 1 given w 0 and capital T. This is the chain rule. P w 2 is nothing but P w 1 w 0 and the whole tag sequence. Finally, we have the two expressions here, P w n given w 0 to w n minus 1 and the whole tag sequence T 0 to T n plus 1. The last expression is P w n plus 1, which is conditioned by W0 to Wn and the whole tag sequence T0 to Tn plus 1. Now, we make an assumption which does not have much of linguistic support. It is more like an engineering decision for the purpose of computation. However, the results of part of speech tagging shows that this is not a bad assumption after all. The assumption in here is that a word is determined completely by its tag. This is inspired by speech recognition. Okay. So, I have uttered a set of words and now I know what the part of speech tag of the next word most likely to be. Okay. And given that that is the part of speech tag which will appear after this sequence of words, what is the probability of a particular word coming there. Okay. So, if I have the sentence I see a black, and now it is clear that the most likely word after black is a noun. So, now what is the probability of uttering I see a black cow, or I see a black dog, or I see a black umbrella. Okay. So, dog, umbrella, cow, all these are nouns which are lexical items. What is the probability they can appear at that position, the last word position, given that the tag there is a noun. Okay. So, these kind of word prediction problems are quite common in the area of speech recognition, and the lexical probability assumption is inspired by. So, if you look at the expressions here, P w given T has been converted into a chain rule expression. After that, by making this assumption that a word is dependent only on the tag at that position, we obtain P w 0 given T 0 into P w 1 given T 1 up to P w n plus 1 given T n plus 1. So, this comes out to be equal to I going from 0 to n plus 1 P w I given T I. Now, this is giving rise to what is called a generative model. If we have this sentence, people jump high preceded by a sentence beginner hat and the sentence ender dot. Then we have here the tag hat for the first symbol, which is hat, and the dot tag for the last symbol dot. In between we have noun, verb, adverb for people, noun, verb, adverb for jump, high, verb, adverb for high. So, you can see that only one tag is the correct tag in the context of the sentence. People is a noun, this noun would be chosen. Jump is a verb, we choose this verb. High is an adverb, we choose this adverb, which qualifies the verb. So, people jump high would get the tags N, V, R, preceded by hat followed by dot. Now, this model is called generative. This model is called generative because you can see that from the automaton we find the words are generated by the tags. It is as if the tags generate the words. That is why it is called a generative model. The second part of the probability expression, the likelihood probability P w given T, okay, which is converted into product of P w I given T I, is the generative model part of the computation, as if the words are generated from the tag. So, we go through this automaton and we have the probabilities of the arcs from tag to tag. This is known as the Bigram probability P t I given T I minus 1, and we have the lexical probabilities, probability of people given n, probability of people given verb, probability of people given adverb. These are the lexical probabilities, and the arc probabilities between two tags is called the Bigram probability or the transition probability. All right. So, when we make a traversal from hat to dot, we find out for every word a tag, and the tag sequence we get is the best possible tag sequence in the sense of being the highest probability path. So, this here shows how the bigram probabilities are represented. This is an important data structure which it is very useful to remember. You see on the column we have the tags NVA, noun, verb, adjective, let us say. In the row also we have NVA. Every cell in this matrix denotes the transition probability. Since it is a bigram probability situation where we say that every tag depends only on the previous tag, we have a matrix where the columns are tags and rows are also single tags. If it was a trigram probability situation, consider a trigram probability situation. Suppose we have the trigram probability situation and we have P of a noun given that the previous two tags were noun and verb. Okay. So, the situation is N V N. Okay. So, when you have this kind of trigram situation, we again have a matrix of transition probabilities, noun, verb, adjective. However, on the row we have the conditioning part which is a pair of tags. So, we would have N comma V, and then we can have V comma A, let us say we can have A comma A. So, what is the meaning of this? The meaning of this, suppose I take up this cell, suppose this cell is our cell of attention. Here we will place the probability of a verb being preceded by a verb and adjective, that is this sequence V A V. Okay. So, the row will have tuples instead of single tags. If it is bigram, then you have single tags on the rows. So, is it clear? The columns will always have tags, single tags. Rows will have pairs, triples, quadruples, n tuple depending on the Markovian assumption we make. Okay. If the assumption is a quadrigram assumption, a tag depends on the previous 3 tags. Okay. So, the whole thing is a 4 tuple, previous 3 tags, and on the row we will have 3 symbols, triples. Okay. So, this is about the transition probability. The lexical probability table also will look similar, it will be a matrix. So, in this situation we have, let us say, noun, verb and adjectives which are on the rows. On the columns we will have actual words. So, how many columns will this matrix have? This matrix will have as many words as there are in the language, or if you want to be more conservative, you can say that the number of columns will be equal to the number of distinct words in the corpus. Okay. So, now if you look at this cell n and people, this is 10 to the power minus 5. This means what is the probability of the word people given that the tag is n. That means, at a particular position, what is the probability that the word is people given that the tag at that position is noun. Now, this how will you compute? You will clearly compute this by finding out how many times the noun tag appears, have it in the denominator, and let it divide how many times does people appear in those noun positions. Okay. So, probability of people given n. So, how many nouns are there in the corpora, and out of them how many are people? That ratio is the probability value. So, this shows that 10 to the power minus 5, which means there are many nouns in the corpus, and people appears once out of 10 to the power 5 nouns. For every 10 to the power 5 nouns, one is a people. Okay. So, this is the meaning of this probability. We can see some zeros here what is the probability of people given adjective. Okay. So, or what is the probability of jump given adjective. Okay. So, these kind of probabilities are very low, almost nil. Jump has never possibly been used in that corpus as an adjective. Okay. So, I suppose this is clear. So, let me just repeat these two data structures once again, they are very important for our understanding. Lexical probability is given by the lexical probability matrix, and in the previous slide Bigram probability is given by this transition probability matrix. Now, how do we calculate these probability values from the actual data? Okay. What have we done so far? Just a recapitulation, what have we done so far is that we have set up the part of speech tagging problem as a sequence leveling task, used argmax computation, applied Bayes theorem to divide it into two parts, probability of prior probability of the tag sequence multiplied by the likelihood, probability of the likelihood of the word given the word sequence given the tag sequence. We applied Markov assumption, and then we obtained P T I given T I minus 1, which is the Bigram assumption. Then we obtain probability of W I given T I, which is the lexical probability assumption. So, Markov assumption preceded by Bayes theorem application, chain rule. Okay. Now, these probabilities gave rise to the transition probability table, also the lexical probability table. Okay. And how do we do the calculation from the actual data? This we will discuss in the next class, but you can see this is a raw piece of text and the whole thing is POS tagged. From the POS tag we record the numbers and then compute the probabilities. We will do this calculation in the next lecture.